As I said, I'm more specifically going to focus on the tropics with just brief foray into these mid-latitude problems. So looking more specifically at the stratosphere-troposphere coupling in the tropics, obviously tropics means we always talk about deep convection and the rising vertical velocities and the waves that propagate upward. When we talked about the predictability issues before, we talked about the zonal and meridional stretching of the winds and how you get things like westerly duct and the tropical upper tropospheric trough, where the tropics can receive signals from the mid-latitude breaking Rossby waves and so on, and tropics can send a signal back, and tropics also do, of course, the communication through the mean Hadley cell kind of circulation, which we just mentioned already in this context of stratosphere. Looking more specifically at these waves, the Rossby waves also propagate upward, and depending on the vertical shear, the same change in the wave numbers and hence the change in group velocities and where the energy gets deposited matters as well. And the deep tropics have these thunderstorms. Very few of them punch through the tropopause, but strongest of the convections and especially hurricanes and so on can, shown here as cyclones, can penetrate into the past the tropopause into the stratosphere, but they can definitely send the waves. The waves then tend to break and then send signals towards the poles, and we already mentioned that the tropopause drops off towards the higher latitudes because the temperatures are cold and the atmosphere is occupying a smaller volume. So you can see these planetary waves then emanating from the convective activity in the deep tropics. So basically they are Rossby waves, and the dispersion relation tends to have beta as a prominent term, which is the gradient of Coriolis in the meridional direction, which makes them planetary waves. So the change in planetary verticity is one of the main restoring forces for the Rossby waves. So remember, for waves you need a perturbation force and a restoring force, so you always look for what the restoring force is. So when we say gravity wave, it's gravity that's the restoring force. Okay, so buoyancy is lifting it up. Let's say gravity is trying to pull it back down. And you also have atmospheric tides, which are related to lunar and solar forcings. And even though we mostly talk about tides in the ocean, atmospheric tides are significant. Obviously we don't feel them much as we do the ocean tides, because the water is heavier, much heavier, 1,000 times heavier than air, of course. And there are gravity waves that are breaking and causing mixing. Every time there is breaking of waves, there is mixing associated with that by the turbulence that is generated. So those propagate poleward, and stratosphere, as we said, is stratified, not so much vertically but horizontally. So you have layered structures, and there is efficient transport, and the residence time of things tend to be longer because you don't have rain and weather to wash them out. So things make it to the polar latitude, so you have the vortex and stratospheric warming caused by these kind of activities as well. So there is a strong coupling, and as we will see, that stratosphere then tends to send the signals back through various processes, not all of which are understood. We will see, for example, that the QBO has a significant impact on convection, which means MJOs, which also means it will be favorable in certain phases, and QBO itself has a eastward and westward phase, and the impact on the troposphere also tends to depend on the phase of the QBO. So these are the coupling processes. This is another way to look at it. This is now showing a very strong deep convection in the deep tropics driving these meridional Hadley circulation, which is part of the semi-permanent convection that occur in the West Pacific and the ITCZ. And you can see that that's hitting the tropopause here, and some cumulonimbus actually penetrate the tropopause and into the stratosphere, inject, for example, humidity, which can make a big difference for radiative balance of the stratosphere. So you have all these communications happening. So there is the Hadley cell, there is communication across the tropopause, and you can see this is shown as a jump in the tropopause as opposed to here where we didn't show that, but there are windows in the tropopause where signals like the potential vorticity from the mid-latitudes can easily come into the deep tropics and so on. So that also allows this communication from the stratosphere into the troposphere through these kind of windows here. So this is the Brewer-Dobson circulation that I mentioned. You can see it's clearly cross-equatorial, high into the stratosphere. This has significance for ozone chemistry as well. So you can see all these nice interactions and the troposphere stratosphere coupling. One of the best examples of the troposphere stratosphere communication and the vertical wave propagation and wave breaking and so on is the quasi-biennial oscillation, affectionately known as QBO. So here is just showing Paul Newman's work and colleagues showing multiple years of observation-based wind speeds from very low pressure levels, which means very high in the atmosphere, 3 hectopascal down to about 300 hectopascal, which comes to about the mid-troposphere or above. And you can see these clear propagations happening over a couple of years. So here is the westerly phase, easterly phase, westerly phase, easterly phase. So you can see that if it can be observed here, then you have plenty of time to watch it come down and then go down into the troposphere. So obviously you expect predictability here, and we will see some surface manifestations of the QBO. So QBO is being triggered by vertical propagation of waves from the troposphere and its impact on the vertical wind structure, and then it's propagating down, as you can see, from the upper stratosphere here at about 40 kilometers down to order 10 kilometers, so just at or above the tropopause, and this is very much focused on the deep tropics. Okay, so you can see that over many years it's very systematic, with some more anomalous event here, a westerly phase touchdown, but then it continued and touched down again multiple times, and this time scale here is the easterly phase is very weak, so there are interactions with other lower modes as well. You can see that here as well. Okay, so this is why we call it quasi-biennial. It's not exactly 2 years, but it is around 2 years. So what are the surface impacts of the quasi-biennial oscillation then? As we said, there is definitely a relation between QBOs, deep convection, and of course surface precipitation. So there are polar routes, subtropical route, and tropical routes for QBO impact between the stratosphere and the troposphere. So that's the Holton-Tan process, which we haven't discussed, but it's anyway communication from a QBO to the stratospheric polar vortex, very much happening in the stratosphere. There is the thermal wind. For example, when you have polar day, or let's say polar stratospheric night, where the months without sunlight are going to make it very cold and set up a thermal gradient from the polar latitudes to the lower latitudes. And if you remember your thermal winds, if you have horizontal temperature gradients like we have from the equator to pole in the lower troposphere, we get the vertical shear and the jet streams. So similarly, you get the stratospheric polar vortex and the thermal wind associated with those gradients as well. Okay, so there is induced meridional circulation. So here we have the subtropical jet that is related to the Hadley circulation and the mean momentum and heat transport associated with the Hadley cell. The subtropical jet, typically these zonal jets are energetic and unstable and zonally asymmetric, and they shed Rossby waves as a result of the instabilities. So you can see these synoptic waves propagating from the subtropical jet towards the mid-latitudes, which create impacts which also come down through onto the phases of NAO. So this interacts with the polar jet stream, and then polar jet stream produces instabilities, and that then pumps PV into the low latitudes through the mid westerly duct and the tropical upper tropospheric trough in the eastern Pacific and the Atlantic Oceans. So NAO is very much an Atlantic Ocean phenomenon. So all those tend to get related. So obviously planetary waves also propagate from the surface into the upper troposphere and into the stratosphere, which are related to generating the QBO, as we said. So this is the tropospheric stratospheric coupling, and there are many impacts not always completely understood. For example, exactly how QBO affects deep convection is not necessarily known. Many hypotheses exist, so that's something you can read up separately. Okay, so let's then come back and look at predictability related to tropical troposphere stratosphere coupling. Just some quick examples, and also touch on some mid-latitude processes that also become predictable because of these same troposphere stratosphere coupling and interaction processes.